In this video, we're going to do a couple more examples of polynomial and rational inequalities. So in the first example, we're going to use a graph to solve a polynomial inequality. Okay, so that's example 2 here. So we have this polynomial, and we want to use the graph to solve where is it bigger than or equal to 0. So we're first going to find where is it equal to 0. Okay, these are going to be the x-intercepts. So 2 times x minus 1 times x plus 3 squared equals 0. So that happens when x minus 1 equals to 0, or x plus 3 is equal to 0, which is when x equals 1 or x equals minus 3. Okay, so that gives us points, x-intercepts, at minus 3 and at 1. Okay, now we can also talk about the multiplicity of these points. Okay, so the x equals 1, the power there is 1 for that factor. So it has multiplicity 1. Because the multiplicity is odd, that means we're going to cross the x-axis. Okay, so we know that it crosses. For x equals negative 3, the power is 2 there. So the multiplicity is equal to 2. So because it's even, that means we're just going to touch the x-axis, so not cross. Okay, so that's going to be helpful. We can also think about the end behavior, because that's going to give us enough information to do a sketch that's good enough to answer this problem. Okay, so when we're talking about end behavior, we want to talk about the leading term. So that means I take the biggest power of x in each factor. Okay, so I'm going to take the 2, okay, the x, and that's to the power 1, and also this x to the power 2. So the leading term is going to be 2 times x to the power 2. So that's going to be 2x cubed. Okay, so that means that the degree is odd. Okay, and the leading coefficient is positive. So that means that our end behavior is going to look like that. Okay, so that's our end behavior. So that means that's enough to graph this. So we know that it leaves this way and it leaves this way. We know that it crosses at 1, but it just touches at negative 3. So it's going to come up like this, just touch the x-axis, okay, at negative 3. I guess we could have found the y-intercept as well, but it doesn't really matter. Okay, so and then it's going to cross up here and leave like that. Okay, so it looks something like that. Okay, this is enough to know where is it bigger than or equal to 0. Okay, so let's do this in yellow. So this is the inequality we're trying to solve. So equal to 0, okay, at both intercepts, but then bigger than 0 along this part of the curve. Okay, so that means that our solution set for this inequality is going to be the number negative 3, because it equals 0 there, and then the interval from 1 to infinity. Okay, so that's the solution set for that inequality. Okay, so for the next ones, we're actually going to not do the graph, and we're just going to look at where can the function switch from positive to negative. Okay, so just to remind you, this can happen at the x-intercepts or the vertical asymptotes. So when you've simplified your rational or polynomial function, you want to find the places where the numerator is 0 and where the denominator is 0. Because the numerator 0 is where the x-intercepts happen, and the denominator being 0 is where the vertical asymptotes happen. And those are the places where it can switch. So we take all of those x values and we put them on a number line, and then we just need to test the value in between. Okay, and that's going to tell us on that interval if it's positive or negative. So let's try this one here. Okay, so first we want to compare to 0. So I want to move the 1 over. So it's going to be a -1, bigger than or equal to 0. And now I want to make a common denominator. So I'm going to times that by 2x plus 4. So I'm going to have x minus 4 and then minus 2x plus 4. Okay, all over 2x plus 4. And then if I simplify that, I have x minus 2x is going to be negative x. And I have -4 minus 4, so that's -8 over 2x plus 4. Okay, and I want to know where is that bigger than or equal to 0. Okay, so this is like so let's call this function the f of x. Okay, so f of x equals 0 when the top is 0. Okay, so that's when -x minus 8 is equal to 0. So that's going to be -x equals 8 or x equals -8. Okay, so that's where we have an x-intercept. Now the function doesn't exist. That's when the bottom equals 0. So that's going to be when 2x plus 4 is equal to 0, which is 2x equals -4, which is x equals -2. Okay, so those are the values that are important. Okay, so this one here is going to be an x-intercept, and this one is going to be a vertical asymptote in the graph. Okay, so then we just make our number line. So let's do it over here. Okay, so I put on -8 and -2. Those are the only places where it can switch, and I'm just going to make a note. So here it equals 0, and here it doesn't exist. Okay, so that might be important. And then I want to test a value in the interval. So let's test -9. So -9, I'm going to have -9 minus 8 over 2 times -9 plus 4. So on the top I'm going to have 1 because I have 9 minus 8. And on the bottom I have -18 plus 4 is -14. Okay, so that's what this equals, but I don't actually care. The only thing I care about is that it's negative. Okay, something between -8 and -2, I don't know, -3 might be okay. You can pick anything you want. So that's -3 minus 8 over 2 times -3 plus 4. So that's 3 minus 8 is -5. And then I have -6 plus 4 is -2. So that's going to be 5 over 2, which is a positive number. Okay, something bigger than -2, 0 would probably be good. Okay, so that's -0 minus 8 over 2 times 0 plus 4. So I get -8 over 4. So that's -2. So negative. Okay, so it's negative in that interval. So now what was the inequality that we wanted to solve? Oops, I went too high. So we wanted to know where is this function. So let's say our initial one. So x minus 4 over 2x plus 4 is bigger than or equal to 1 when -x minus 8 over 2x plus 4 is bigger than or equal to 0, which occurs on the interval. Okay, so it's when it's positive. So that's going to be this middle interval here. And we're allowed to equal 0. So that means we can include negative 8, but we cannot include the endpoint negative 2. So it's going to be the interval from negative 8, including negative 8, to negative 2, not including negative 2. Okay, so cannot include x equals negative 2 since it does not exist there. Okay, so that's our interval. Okay, let's try another one. Okay, so we're going to do a similar thing. Okay, so first we start by shifting everything to one side. So it's 5 times x minus 3 minus 3 times x plus 1, and that should be bigger than 0. Okay, now I want to make a common denominator, so I'm going to times this one by x plus 1 over x plus 1, and this one by x minus 3 by x minus 3. Okay, so that gives me, if I expand everything, so it's going to be 5x plus 5 minus 3x minus 9, okay, all over x plus 1, x minus 3. And I need that to be bigger than 0. So if I simplify that, okay, the negative has to go through. Okay, so it's 5x minus 3x, so that's going to be 2x. And then 5 plus 9 is going to be plus 14 over x plus 1, x minus 3. Which we could, if we wanted, we could pull out the 2. So it's actually x plus 7 on the top, just to make sure that nothing is going to cancel out. Okay, so that's what we want to solve. Okay, so what we want to do is say, okay, well, let's call this thing f of x. Okay, so we want to solve f of x bigger than 0. So we want to find where is it equal to 0. Okay, so that's when the top is 0, which is going to be when x plus 7 is 0, which is going to be x equals negative 7. Okay, so that's an x-intercept, or that's the x value of an x-intercept. Okay, f of x doesn't exist when the bottom is 0. So that's when x plus 1 is 0, or x minus 3 is 0, so that's going to be x equals negative 1, or x equals 3. Okay, so those are the values we want to put on our number line. Okay, so let's make the number line down here. Okay, so the smallest one is negative 7. Okay, and then it's negative 1. And then it's positive 3. Okay, so you always want to put them in order, and I like to make a note here. So this one is equal to 0, and these two don't exist. Okay, so I remember I don't want to include those ones in any interval. Okay, so now we just have to try a point. Oops, normally I do this in green. So maybe we try negative 9. Okay, so that's going to be, if I plug in, so it's going to be 2 times negative 9 plus 7 is negative 2 over negative 9 plus 1 is negative 8, and negative 9 minus 3 is negative 12. Okay, so that means that the top is negative, because it's 2 times negative 2, it's actually negative 4. The bottom is positive because it's a negative times a negative. So this whole thing is going to be negative. Okay, remember, I don't actually care what the number is. I only care if it's positive or negative. Okay, now something between negative 7 and negative 1, maybe negative 2. So it's going to be 2 times, so negative 2 plus 7 is 5. negative 2 plus 1 is negative 1, and negative 2 minus 3 is negative 5. Okay, so that's going to be positive over positive, so this is going to be positive. Okay, between negative 1 and 3, I could use 0, so it's going to be 2 times 7 over 1 times negative 3. So that's positive on the top, positive times a negative on the bottom is a negative, so that's going to be negative. Okay, now 4, so that's 2 times 11 over 5 times 1. Everything's positive here, so this is going to be a positive number. Okay, so now we want to look, where is the function strictly positive? Okay, so that's going to be on this interval and on this interval, where we get the positives. Okay, so the solution set is going to be the interval from negative 7 to negative 1, and then again from 3 to infinity. Now I don't want to include any endpoints here because the inequality is strict. Okay, so I don't want it to be equal to 0, so that gets rid of the negative 7, and I could never have included the negative 1 or the negative 3 because they don't actually exist there. So that would be our solution set here. Okay, we have one more example to do. What's the domain of this function? Okay, so we need, obviously, the thing on the inside, x to the 4 minus 81. We need that to be bigger than or equal to 0 in order to take the square root. Okay, so now we want to solve this inequality. So that's our f of x. So we want to find where it's 0. Maybe I'll just call it f of x. Okay, so f of x equals 0 when x to the 4 minus 81 is equal to 0. Okay, so we can factor this, so it's a difference of squares because it's x squared squared minus 9 squared. So it's going to factor as x squared plus 9 times x squared minus 9. Okay, now the second factor there is also a difference of squares, so we can factor it even further. X squared plus 9 times x minus 3 times x plus 3. Okay, so that's going to be 0 when one of these factors is 0. Okay, now x squared plus 9, if you move the 9 over, is x squared equals minus 9. Okay, that has no solutions. The square is always positive, so we can never get a negative number. Okay, so the only places where we equal 0 is going to be negative 3 and positive 3. Okay, so we can put those on our number line. Okay, so negative 3 and positive 3. And then we just want to check a value, so negative, I could use negative 9, but let's do something like negative 4. So I want to plug those in. Now x squared plus 9, I'm going to write a note here, down here. X squared plus 9 is always bigger than 0. Because x squared is bigger than 0, or bigger than or equal to 0, and then I add 9 to it. So I actually, that thing's always going to be positive, so I'm just going to write it as a positive. Okay, now x minus 3, that's going to be negative 7. X plus 3 is going to be negative 1. So I have a positive times 2 negatives. This interval is going to be positive. In the middle here, I'm going to use 0. Okay, so the first thing's always positive. And then I have 0 minus 3 is negative 3. 0 plus 3 is positive 3. So I have a positive times a negative times a positive. So one negative is going to be negative. If I use positive 4, okay, the first thing, x squared plus 9 is always positive. and then I have a 1 and a 7. So I have 3 positive numbers multiplied together, so that's going to be a positive number. So we want it to be at least as big as 0. Okay, and at -3 and +3, it's equal to 0. So we want these two outside intervals. So the domain is, I shouldn't have called it f of x actually, because the original function is called f of x, but I'll switch that in a moment. So the domain is going to be, in interval notation, -∞ to -3, including -3, because the square root of 0 is 0. Okay, so you can evaluate it at -3, and then including 3 to infinity. So that's the domain of f of x. Okay, now I'm just going to switch. Sorry about this. I'm just going to call that g of x, just so it's not the same name. Okay, because it is different. We're just talking about the inside bit. So we want to solve g of x is bigger than or equal to 0. But everything else is the same. The name I wanted to change, so it makes sense. Yeah, so that's how you solve polynomial and rational inequalities. So you can either use the graph, or you can just find the x-intercepts and the vertical asymptotes, and then use a number line check in each interval.